sorry, Tuka.
No, that's all right. Okay, yeah. So depending on how that line is bent, you get different values on this y-axis for each of the features in the model. So features are colored according to which modality they're coming from. So the yellow are the physiologic smartwatch features. The green is the audio, and the purple is from the text transcripts. And if I go through them, for the most part, the physiologic signals, such as movement and posture, as indicated by PPG and accelerometry, indicates, whether the individual is sad. Those are most predictive of sad stories. And audio features, so the more their energy there is in their voice, or the more they're speaking, and this is another energy one, so the more energy there is and the more they're speaking, the more likely they are to be happy. And as you'd imagine, the more they use negative words in their vocabulary, in their speech, the more likely it is a sad story. So what was really nice when we saw this was that, yeah, it matches sort of the intuition. If you were to handcraft features, yes, the more negative words they use, the more likely they're to be sad. The less movement or the particular movements that they're having tend to be indicative of sad stories. The more energy they have in their voice and the more they're speaking, the happier they are. So those were the 10 features we found. And we also evaluated, there's several different models, sort of these bag of models that we could use, that we could end up using to evaluate our system. And I think what you should take away from here is that this is sort of like an accuracy score, but not exactly. So I should say this particular, there are many different metrics that you can use, and this ties into, you were asking about R-squared score, or what metrics to use. So there are many different metrics that one can use. And you can imagine in a scenario when you're having a conversation with an individual, if you say something where the interaction ends up being a negative interaction, that's a lot worse of an event than saying something and the interaction leads to a positive outcome. So you want to avoid negative outcomes far more than you want to create positive outcomes.
Falsely predicting. So this is a 2x2 grid. It's actually pretty simple. Let me draw it here so it's clear to them. And, so that you know why we didn't just use simple accuracy when we were trying to say that instead. Okay, look, there's only 4 blocks on this, right? There is, I predicted a, happy, and then I predicted sad, right? And then there's what happened what's the truth, what actually happened. And then there's, the truth was happy, the truth was sad. Well, what Tuka is saying is that if I predict sad, but it's actually happy, that's not the same as, predicting happy when it's actually sad. Those have different costs. You can think about, this is a classical thing that comes up in medicine, for example. Let's say your grandpa is plugged into heaven forbid, he's plugged into a machine at the ICU. And the doctor comes and says, well, we got to make a decision about whether we unplug him or not. Well, again, it's a 2x2 grid. Unplug, don't unplug. But the problem is, if you unplug him too early, that has a huge cost. So a mistake one direction is not the same as a mistake the other. So this is like accuracy, but it accounts for the differences in those costs. Okay? That's the idea.
Can I ask you a technicality there?
Yes.
Why will you measure performance in AUC and not R-squared, like typically in time series?
Wonderful, because for classification problems, where you have an outcome which is 1 or 0, area under the receiver-operator curve is actually the metric you want to use. Assuming that you can't assume that the classes are equally costly. So again, that's the thing I mentioned about the grandpa example, right? Unplugging him too early is not the same as leaving him plugged in for too long, right? Those are both mistakes. Leaving someone plugged into the ICU is a mistake if it's too long, if he's not going to wake up. But it's not the same cost as unplugging him too early. So because this thing accounts for that, that's the reason we chose that metric. Does that make sense?
What would be the highest cost in this grid, let's say?
Yeah. So actually what's really brilliant about the AUC is it integrates across every possible cost. So it abstracts the problem away. What you can also do is you can say, let's assume that the most horrible thing in the world is to do this. You know, I don't want to, let's put a cost in here, how bad it is. Let's say that if I predicted happy and it was sad, let's say that this is, this is okay. This is 0. If I predict happy and it's happy, this is good, I get +1. If I predict sad and it's sad as this is +1. And I predict sad and it's actually happy, now the person feels awkward or something, and this is, -3. So you can set a specific value like that. And then you can optimize your classifiers, these machine learning algorithms. We can show you how to do some of that in the interactive coding session if you'd like. You can set a matrix like this and say, this is my assumed cost. This is 4 times worse or 3 times worse than this if you make this mistake. And then the algorithm, the parameters Tuka showed you on the bar chart thing, which said, oh, here's how important this one is, those will all adjust. And they'll say, oh, okay, given what you've told me now, I'm going to set it like this when I'm making my predictions, because I don't want to screw up according to the metric you gave me. So you can set those. Does that answer the question? This AUC is very nice because basically it says, I'm going to just basically integrate over every possible way of setting this thing. So if this is, totally fine, and this is super costly, this is super costly, and this is totally fine, it checks all of them, and it gives you one number, which is why we reported that.
And if you get a AUC score of 1, that's perfect. If you get a score of 0.5, that means it's random, the performance of your model. And also the idea here is that if you're a computer science or you're an engineer, you're not a policymaker, you're not a decision maker, you're not a medical doctor. You shouldn't be the one to decide what the costs are of the intervention or the mistake or anything like that. So really the best way to operate if you have your engineering cap on is to say, I'm not a policymaker, I'm not the decision maker here. This is how well my system can perform given all your thresholds of risk that you want to take. So that's why we tend to prefer report